Hello, I'm Richard with EV4U Custom Conversions, and welcome to another one of our videos. And in today's video we're going to address a question from a viewer, and based on the question he wanted to know what is, or wanted us to discuss, SOC, SOH, and C rate. So I'm assuming that because he asked the question, he already knows the answer. But we appreciate the suggestion for the video. We've touched on all of these things, I believe, in previous videos at one time or another. We've got over 300 of them. And I think we've been doing the videos since 2008 or 2009. But this is a good suggestion and a good opportunity to address this again. So, what is SOC, COH, and C rate? Well, we'll address them one at a time, and we'll start with SOC. And SOC is just short for state of charge. And the state of charge is referring to the state of the charge of your battery pack typically, but you reduce it down to the smaller level, be the state of charge of a cell. But either way, it's the percent of capacity remaining. So 100% state of charge means that it's fully charged. And if it's 50% state of charge, it's only half charged. So, example I use right here, 80% state of charge means that 80% of the usable capacity is available, or you have consumed 20% of that total capacity. Okay? So that's state of charge. Well, before we get on to the others, let's talk a little bit more about, we're talking about the state of a charge. What's a charge? We're just assuming that we all know what we're talking about. And I think it's common when we're talking about EVs and we think of state of charge, we're relating it to the fuel gauge, our gas gauge, or fuel gauge, and that it's a percentage, 3/4, half, quarter, that type of thing. But we're not talking about fuel as in gasoline or diesel. We're talking about energy in the form of electrons. So a charge is what we're going to talk about. And the unit of charge is the coulomb. And a coulomb is 6.25 times 10 to the 18th power electrons. So it's quite a few electrons make up one coulomb. So, big deal, you say. What's a coulomb? You told us, and we still don't care. So, will you ever hear of amps, volts, or watts? Those are things that, in the conversion world that you'll hear mentioned. And so, you might say, well, what's a watt or what's a volt? Well, we're going to get to that. But we're going to look at it in relationship to, how are they related to a charge? And you'll find out that the common denominator here is a charge. It's that building block. No charge, we don't have any of the others. So no charge, we don't have a state of charge. So let's look at how volts, amps, and watts are related to charge. We'll start off with amp, which is short for ampere. And most of these are named for somebody. And we're not going to go that much into it. But the amp is the rate of flow for a charge. Okay? It's the unit of electric current. And current is that rate of flow of a charge. So when we talk about amps, we're talking about the rate of flow of current in a circuit. So when the charge moves at a rate of 1 coulomb flowing past a given point per second, excuse me, the value of the current is 1 amp. So we've got 1 coulomb flowing past a given point per second. That's 1 amp. So now we see how the charge and the amp are related. And the watt, we all know watts with light bulbs, watts with the kilowatt hours and kilowatts and things like that. People throw the terms around. But a watt, again, named for a person, is the unit of electrical power. Just like horsepower is a unit of mechanical power. So the watt is a unit of electrical power. And 1 watt of power is equal to the work done in 1 second by 1 volt of potential difference in moving 1 coulomb of charge. So there's that coulomb again. And 1 second. You see kind of commonalities here. What we haven't talked about is potential difference. You have to have potential difference in order to move a charge. So let's take a look at that. And of course, the unit of measure for potential difference or electromotive force is the volt. And volts equal to the difference of electric potential between 2 points on a conducting wire carrying a constant current of 1 amp when the power dissipated between the points is 1 watt. And so it's the measure amount of work required for moving 1 coulomb of charge. That's that electromotive force that's required to move 1 coulomb of charge. And that's 0.7376 foot-pounds of work is necessary to move 1 coulomb between 2 points is 1 volt. So when you have that much work being done to create 1 volt, to move that 1 coulomb. So let's take a look at that in a little different way. We've seen it textually, but let's look at it, graphically, and maybe it'll kind of mean a little more to us that way. So here we are with a little graphic. We're showing our cell here. This is 1 volt. This represents 1 volt of potential difference. Okay? And it's moving this 1 coulomb per second through this circuit. In other words, it's moving 6.25 times 10 to the 18th power electrons flowing past this point in 1 second, creating 1 amp of current flow. And it's doing enough work to produce enough power to produce 1 watt. And we know from, I get called on once in a while when I use Ohm's law, actually incorrectly. I just use it as a generic term. Everybody's heard of Ohm's law, it seems like, but not many people have heard of Watt's law. And this is technically part of Watt's law, is that volts times amps equals watts. But we can see it here. we looked at our definitions, and you can see that 1 volt times 1 amp equals 1 watt. And we got these directly from our, our definitions. So 1 watt of potential difference, moving 1 coulomb per second past a given point, is 1 amp. And to do that, that's the amount of work to create 1 watt. So moving on, in a conversion, the state of charge can be calculated. So we've talked about what state of charge is, what the charge, but let's kind of back to how this all relates to our conversion. So the state of charge can be calculated by measuring the current flowing in and out of our battery pack. Okay? And by measuring the current versus the time, as well as the voltage, we can come up with the power, or actually power over time, which would be watt hours consumed. And that's what we want to know. That's how we figure the state of charge, is by measuring the coulombs in and out of that battery pack. Okay? So watt hours is just amp hours times the voltage. So again, volts times amps equals watts. And you hear the term kilowatt hour. Kilo is just 1,000. So a kilowatt hour is 1,000 watt hours. So by measuring the current versus the time is how we come up with this, but we have to have a way to measure these things. So we can measure the voltage, and we can measure the current, and we measure the current using either a Hall effect or a shunt. So a Hall effect sensor will measure the current passing through a wire, and a shunt basically is a known resistance, and you're measuring the voltage drop over that known resistance, and that's how we're able to then calculate the current flow past that point. So either way, that's going to give us the current, and then we're going to have the instrumentation that's going to, measure that current, measure the voltage, and keep track of the time, because there's the time element. So it's got to have an internal clock. And so that's what the instrumentation does. It's going to measure all those things and give us either amp hours or watt hours or kilowatt hours, however they scale it or measure it. But it's giving us power over time, which will then give us the state of charge. Now another one that wasn't part of this guy's question, but it goes hand in hand with this, and that's DOD, or depth of discharge. And depth of discharge is just the inverse of state of charge. So if the state of charge is 20%, that would mean that the depth of discharge is 80%. Okay, or in my example here, if the state of charge is 40%, then the depth of discharge is 60%. And we're going to talk about depth of discharge in a moment here. But next, let's talk about SOH, state of health. This is where you get the battery to stick out its tongue and you take its temperature. No, actually, it's just the condition of the cell stated in a percentage based on what it's rated. Okay, so if it's rated at, you'll see a bunch of different factors, but if it's rated at a certain number of amp hours, for instance, then that and it equals that, then it would have 100% state of charge or state of health. A state of health is going to be a percentage related to however they're going to, whatever factor they're going to use to determine that. Let's take a look at this so you have an idea. State of health does not correspond to a particular physical quality. Okay, this is where it's where I was fumbling around here. You'll see in a moment. There is no consensus in the industry of how state of health should be determined. And so different battery manufacturers, different BMS manufacturers, they all come up with their own determination of how you determine the state of health of their cells. So the designer of a battery management system may use any of the following parameters or combination to derive an arbitrary value for the state of health. Arbitrary. Multiple parameters. So if someone just says this is the state of health, well, you're going to want to know more information. What parameters are they using to determine that? It could be internal resistance, impedance, conductance, the capacity, which I was referring to, the voltage, self-discharge, the ability to accept a charge. And here's one that a lot of battery manufacturers state, and that's the number of charge-discharge cycles. We're going to talk more about that. The age of the battery, the temperature of battery during its previous uses, or the total energy charged and discharged. And there's others, but those are just some of the parameters that people that are discussing state of health of cells will use one or more of those parameters to come up with that percentage state of health. So we talked about charge-discharge cycles, better known as life cycles. Life cycles is the number of charge-discharge cycles, okay? And so a lot of battery manufacturers will say that, it has a life expectancy of so many life cycles. And then they'll specify what they consider a life cycle, because that's not universal either. But a lot of them use the 80-20. So in other words, they take it from fully charged down to a 20% state of charge or 80% depth of discharge, and that's a cycle. So there's two things, and I don't think you hear this very much, but anyway, there's two things. There's a lot of things that will affect the life cycles, and then the state of health if you're using life cycles as a measure. But they're the two things that affect it the most, and you probably don't hear about that. And one is the depth of discharge. So, they'll give you, for instance, say 3,000 life cycles at 80% depth of discharge. Well, there's another part in there that they don't relate typically either, and that is they consider the life of those cells when they have 80% of their original capacity. So say you had a car that originally had a 100-mile range and now it has an 80-mile range. That's, you have 80% of the original capacity. That's the life expectancy right there of those cells in automotive application. And so what's going to affect those? Well, they're going from fully charged, like I said, down to 80% depth of discharge and back to a full charge. And they're going to get, say, 3,000 life cycles. Well, what they don't tell you is that if you only discharge it down to 50% state of charge or depth of discharge, the life cycles then goes up, and you're going to get 1.5 to 2 times the number of life cycles you got at 80% depth of discharge. It's one of those things that I don't hear people talk about that, but if you know that, you're like, well, maybe I should be charging my car every day or every other day instead of letting it get, so deeply discharged. Because if you don't need to deeply discharge it, that's going to affect your life cycle. Now, whether or not you're going to keep the car long enough and all that to ever notice, that's a variable also. But that is a main factor in the number of life cycles that you're going to get out of a cell or your battery pack, is the depth of discharge. And then the other is the rate of discharge. So if you're a hot rodder and you're always hammering that accelerator, that affects your life cycles also. So those are the two things that affect life cycles the most: depth of discharge and the rate of discharge. Okay, C rate. This was the last one that he had asked about. And C rate's just simply the capacity rating. Okay, and they're going to use the capacity rating to give you an idea of the cell's performance capabilities. So, used to specify the rate of charge or discharge of the cell. Okay, how you can treat it, how it will perform. So, an example: you have a 230 amp hour cell, like what we use, the Cal cells. They're a 230 amp hour cell. Well, 1C, so basically 1 times the capacity rating, 1C, would be 230 amps. 2C, 2 times the capacity rating, 460 amps, if I did the math right. And then 0.5C is 115 amps. So when they're talking about, a C rating, they're talking about the capacity rating, but they usually are referring to it in regards to the charge and discharge rates of the cell. And so you can have a cell that has a maximum discharge rate of 2C, or 2 times the cell rating, and they typically give you a continuous or momentary or 10-second kind of thing. And so this is just arbitrary here. So my little example here, maximum discharge rate would be 2C, and you can discharge at 8C for 10 seconds, okay? So with the 230 amps that we were talking about on the last slide, that would mean that you could have a continuous discharge rate of 460 amps. Now, when doing a conversion, you'll learn about, how that battery pack capabilities need to be matched to your, motor and inverter. And we talked about that in the workshops. So they will also give you the maximum charge rate. In my example here, saying 1C, so that would be a maximum charge rate of 230 amps. So that is kind of, state of charge and state of health and C rate. I'd say in a nutshell, but I kind of expounded a little bit on it. But hopefully this kind of clears things up for anybody that was wondering. Like I said, you'll see C rate and you'll see state of charge much more frequently than you'll see state of health. But all are important. Like I said, in designing a system, you want to definitely be mindful of the C rate. And one of the things that we get questions for once in a while is, we do a lot of stuff with solar, and there are people that are looking at these batteries that are basically designed for solar, and they're wanting to know if they can use these in a conversion. And typically the answer is going to be no. Most of them are what even the manufacturer, they call them a deep cycle battery. And in the EV world and in the conversion world, we want what's called a traction battery. And so a lot of those, like, well, there's just so many brands out there. Right now, I'll just use one that comes to mind, Battleborn. You know, a lot of them have fairly low discharge ratings. So even though they may be using cells that have a much higher individual C rating, their C rating may be, you know, continuous 200 amps, but the battery that they're building, if it's a 12-volt battery, they're basically using 4 cells, typically lithium iron phosphate, because it gives you voltage that's most similar, out of all the chemistries, gives you the voltage most similar to a lead acid battery. So 4 lithium iron phosphate cells mimics a 12-volt lead acid battery. And most of the cells they use, if you were to take them out and use them individually, they would have a much higher C rating. But they're built in this battery, and they typically have a built-in BMS and everything, but it's their interconnects and their BMS and everything is the limitation. So I have Battleborn batteries in my fifth wheel trailer, for instance, and the maximum discharge current, if I remember correctly, is 100 amps. Okay? So, or at least continuous discharge current, it's 100 amps. But I know that the cells inside are capable of much more. And so that's why you can't use those batteries in automotive purposes, because unless you're doing enough of them in parallel as well as series, and a lot of them don't allow you to series more than, you know, 3 or 4. And so you wouldn't get up to the voltages that we use in the automotive, scenario. So that's why, you know, knowing the big picture, you know, so if you go out and you're doing a conversion, you're saying, oh, I can buy these batteries, they're nicely packaged. Some of them are fairly reasonably priced. Battleborn's not, but there are. I've got SOKs in the Doka. They're much more reasonable. Those are, I think, 206 amp hour batteries. But anyway, 12 volts. They're not designed for use in an automotive realm. They're not designed to supply the current needs required for conversion. Well, anyway, hopefully this gives you some insights to state of charge and state of health and a C rating for cells used in, you know, I get questions a lot of times or statements where somebody will say, you know, using your range formula, that's just an example, where people can't seem to follow the topic, and that is, they're like, you know, my Tesla gets much better range, you know, if I use your range formula. Your range formula doesn't work for my Tesla. Well, as a reminder, folks, EV for you is not about EVs in general. It's about conversions, about converting an internal combustion vehicle to electric. That's and how to do it safely, simply, reliably, and affordably. That's what we do at EV for you. So yeah, our formula isn't about factory-produced electric vehicles, and it's not going to be accurate for them, but it's pretty dead on if you're doing a conversion. And so the information that we give may not be a blanket information that you got to maintain focus. And our focus is on conversions. And so we try to give you information that will help you in that endeavor. And unfortunately, YouTube videos, they're short and they vary and everything. So if you really want to be serious and you want to do a conversion yourself, or perhaps you want to start a little side business, or we have a lot of people that take our workshops that are already in the automotive industry and they're looking to add to their existing business. Point is, YouTube videos are the tip of the iceberg. They're not going to give you all that you need to know, and in a format that is really conducive to you learning what you need to know to build a safe, simple, reliable, affordable conversion. Or you can take the affordable out of it. I mean, that's our focus. But, you can add bells and whistles and complexity and everything else. Once you understand the big picture, then sky's the limit. And that's what we're here for, to help you be able to shoot for the stars. So if you have any questions or comments, info@evforyounow.com. Be glad to answer any questions, comments. You can leave those, please. We also are appreciative if you would subscribe. 80% of our viewers aren't subscribers, and that's because until recently we never said anything about subscribing. So if you're going to watch, why don't you subscribe? We'd appreciate it. See you next time.